Is being recorded.
Okay, so my name is Rohit Sharma, and I'm going to talk about AI in EDA. This is kind of a dry topic. Would like to know how many people are from semiconductor design or design automation. Show of hands. That's very good, Stan. Thank you. So I plan to keep it interactive, and as and when you have questions, feel free to hands, and I will try to answer or foster the conversation. This in no order. I will go through slides. This is about me. I started working 2000, spent close to 20 years developing software. I've worked for TI, Magma, Apache, and now I'm working for IIT. During a couple of months, and if you want to reach out to me, these are my social handles or talk to me afterwards. And I've been living in Bay Area for about 20 years, married with 2 kids, high school going. So with that, let's move on to the topic. So AI, right? Everybody's talking about AI. Why is it important? Why is everybody so excited? There's so much media coverage about AI in every industry. Everybody seems to be talking about it. And I'm on the red wagon where, yes, you should know AI. Even if you're not using today, you should know maybe you would need it tomorrow. And famous people like Andrew Ng and Jeff Hinton have gone on to say it's new electricity is going to disrupt many industries. It's new oil, data is new oil, and AI is new electricity. So it's a fourth industrial revolution. Um, I'm still sitting on the fence whether it would be or would not be, but still being called a fourth industrial revolution because of the disruption it's going to bring to many, many industries. And I will show the numbers on the slides. On the right hand side, these are some of the industries that you see that would have some kind of influence on AI, whether companies, whether they choose to grow with AI or without AI. The growth with AI would be multiplied, and without AI, they will have to probably find their niche in some way or another. Um, so jobs and sectors are definitely going to be impacted with AI in some form or the other. And so AI is fast becoming the central tenant for disruptive changes. Now, down to the numbers. So this is a report from Accenture. Um, and essentially, it's a comparison at a macro level. Where they are looking at 12 countries, and those countries contribute 50% of the entire global baseline gross value. And from United States to Spain, and the two bars that you see side by side, the orange one is a baseline where they are projecting the economy will grow by this much percentage, and the one with purple is with AI, where the AI effect of AI has been absorbed. So the growth in every case in every country is anywhere from 130% to over 100% with the effect of AI. And this is 50% of the entire global GDP that we are talking about. So this is macro trend, and you're looking at from 2000 from now to 2035. So this picture itself that comes from Accenture, and this is a large report, like 800 pages or something, very detailed analysis. This is a summary I thought would like to present that tells you scale that AI would affect in your daily lives, your jobs, the way you live, and in future. So Accenture analysis across 12 countries and together generate more than 50% of world's economic output. Um, and this slide actually captures that effectively. Now, coming down to design automation, AI has been automating pretty much everything, all industries, walks of life, the way we live, smart homes, smart offices, smart cars. But the industry that has been automating the VLSI design is still struggling to find a successful application with AI and ML. And while both of these will grow, one will grow at a much faster rate than the other, both of them are on the growth trajectory. So AI, ML will add 20 trillion to the global economy by 2025, another report that runs on the side, right? And design automation market will hit 14 billion from 6 or 7 billion today, which is also a good growth. This number again comes from the GMI report. So both of these industries are growing at a different rate. Now the question really becomes, can EDA really capture the exponential growth of AI? Are we equipped? And what are the challenges? So we looked at this 4 or 5 years ago when I started Paripat. Some of the challenges that I'm going to share are technical in nature, also business as to in terms of user adoption and the hurdles that you will face while you're adding a feature or a product or something new in your flow. The kind of questions you would expect. So the answer to that question is definitely a yes. It can, but one of the first challenges is look at the research rate. EDA, and when I'm saying EDA is electronic design automation, it's not exploratory data analysis. In AI, these two are same acronyms. So differentiation I'm talking here is design automation. With that, the last year alone, the number of papers published in deep learning, and the references on the side where we used Science Direct APIs to pull the data, over 100,000, just in the deep learning, and doesn't count machine learning. And EDA is not large enough to, even if it deploys all the spend, about 20,000 people, they will not be able to read, that many papers. So, and not everybody is working in development. So, given that, that's one of the challenges. And also, the research, the budget is phenomenal. Even though it's 1%, this total research does not include the industrial or private sector or public companies. This is just universities and pure research institutions. 1% in any one field is large. So it can. So now, how do we do that? How does EDA, how does the design automation use AI or deep learning research? Now, some of the observations here, and the first one is the change would likely come in the form of features, not products. AI, even though it's a large technology, does not make enough impact on the EDA flows to bring out a disruptive change that it does in other industries. And there are several reasons that I'll go through. So definitely it has a place in EDA. The change would likely come in the form of product features, not new products or flows. And that so far has held. I made that prediction 2 years ago. There are companies that are coming up in EDA space, but either not well funded or not making enough distinction compared to existing products. And number two is AI features will bring usability, accuracy, and performance. All of that will be incremental. It won't be jump that requires a startup. So again, the summary, AI won't bring a disruptive change in EDA unlike other industries. And so while we were working on our product, this is the infrastructure that we need to think through when you are developing a new product from scratch. So you would be looking at mathematics, including, and this I'm talking about going back to 2014. TensorFlow wasn't there. There was a software called Octave. I don't know, many of you may not know, but that was the cornerstone of AI at the time when it comes to free software. So we ended up developing most of this. Today you can use some of these free online frameworks, but they have grown so complex in their structure, in their structure itself, that they are branching out. For example, TensorFlow has 6 different repositories alone to cater to different either applications or browsers or other TensorFlow Lite, TensorFlow JS, TensorFlow main, and the one is targeted for GL, I think. So the point here is it's a complex infrastructure that you will end up either understanding or developing yourself. Understanding TensorFlow or PyTorch for that matter is not an easy task. So they are large software. You'll have to deploy multiple engineers just to bring them to your infrastructure. So this is one of the challenges. And what we did was to find out if we can do a classical, can we solve a classical problem using machine learning? And the classical problem was to train a machine learning model and classify the type of items fully expected netlist. And this is a generic problem in computer science to find a pattern in a design. And it's been solved using heuristics before. Some of them successful, some of them not as successful. DRC's application, $100 billion in revenue. So if you find a successful application of this, which exceeds in accuracy or performance, or both of them, then you have a chance. So that's where we started. Can we find? Now we'll talk about the challenges we went through designing. At a very high level, this problem essentially is NP-complete. On the input side, you have fully extracted netlist, and the model is going to look at that netlist and tell you whether this is a full adder or majority gate or. And for this, the database we took was data set was about 12,000 small cells from different libraries of the same process node. Any questions? I am, like I said, it's going to be. If you have a question, feel free to ask. And there are like a couple of more slides on this problem, then we'll be questions again. So what is VCC? VCC is a VLSI circuit convolution. Essentially, we used convolution in a different sense, just like CNNs use convolution for images, we used convolution for circuits. So VCC is a common design automation problem used for detecting patterns in ASIC, ENS, and custom flows. And it is a pattern detection algorithm in its generalized form and applicable to many other like extraction, DRC, simulation, and convolution. For those of you who don't work in the backend or simulation, it's been used in circuit simulation for many years. So it's not anything new to EDA or design automation people. Right?
Question. You mentioned earlier the AI's contribution to EDA is largely the feature improvement. Right? As the feature improvement manifested value from a new capability of the product, new business model, can you comment on this?
This model part, I haven't seen that yet. So there are efforts from Cadence and Synopsys both. One of the successful ones is in the verification domain, where they're looking at test bench generation and tying that to the coverage. And so sort of sorting your test benches, generating and sorting your test benches to give you the top 10 or top n test benches to give you 90+% coverage. And that takes less time. So both of these companies have that feature in their product. It's just a feature. I'm not aware about their licensing model, so not really sure. And then there are other small companies like under $1 billion funding that find machine learning. But my prediction is it's a difficult problem, not because of the technology. It can be applied. One of the main point is that just because you can solve a problem using deep learning does not mean it's a good idea to do so.
Is there a right training data set for this particular area?
So that depends on the problem you're solving. Right? EDA has a large flow from front end to the back end, and every product will have different problem and hence a different data set.
Mostly bounded data sets, all right?
Bounded in what sense?
There's more predictability in what the data is create from an outcome perspective.
Right, I would agree with that and disagree with that. I agree in the sense that because this data comes from software usually don't tend to make mistakes as much as humans do. So there is not much to clean when you're looking at the data set. If it's a def output, for example, it's going to be generally, syntactically correct, 99% of the time. And given that, there's not much to clean, so you can be, certain that you don't have to look at or spend your time in EDA. At the same time, are you covering the entire spectrum? That is a difficult problem in itself. And I'll explain that in slides.
When you mentioned BCC, are you talking about power routing or something else? BCC is a common design automation problem. Are you talking about power distribution?
So this is actually a pattern detection problem. This is VLSI circuit convolution, that we have named as BCC. This is not that BCC. Yeah.
So AI has many applications. So the question that you mentioned about the feature, because the university is not asking for the question, because applying technology to an application where there is some plot missing. So if they are going to for similar type of approaches as before, what is the problem?
Right. So that problem essentially should be looked at by the business managers as to whether they are asking the right question or not. Right. Sometimes, and you might have heard this too, customers don't always know what the problem is, the problem they're facing, and it's up to the developer or business manager to identify that and solve it. Customer is always right. They want a solution. They don't know what form the solution will take, and that's up to you. I lost the second part of the
Yes, yeah, so basically, through the years, EDA was driving the innovation. Basically, we're coming up with the ideas and then automating and then the design houses. But now that piece is missing because they haven't figured it out yet.
Right.
And so when you set the feature application, they're not responding along the way. Okay, they haven't asked that question. That could be one.
That could be one possibility, but when I say this, I'm not saying that from their point of view. I'm saying that from the technology point of view. Whether how much change does the application of AI algorithm can bring to a product? And generally, users, the adoption is not because you have a product that uses machine learning. It's because it has a value to it. So like 10 times faster, 10 times less memory, 2% more accurate, right? Something like that. That saves them money or time. If it's doing the same thing, and if you're using deep learning, nobody's going to buy that, right? And give you an example, prime time, for example, the factor in the industry standard for almost 15 years now. You can do the 99% of the same critical path prediction using deep learning by creating a version of model on a node and define a problem live and you see 99% accuracy. Not going to do that. The reason is when somebody is taking out their design, they are looking for 100%. User would, and if you tell them that this methodology is probabilistic, the companies that have come 10 years before have failed precisely because of that. Back in mid 2000, there were companies doing statistical timing analysis. None of them succeeded. There are some tools that are doing statistical timing analysis. Adoption is fairly painfully slow. People are even at 10 nanometer using STA, static timing analysis, comfortably. So would not be 100% sure. Factor that kind of was a roadblock for the adoption of that technology, I would believe was major of probabilistic results. So that was
Question.
sure.
Single and self-employed here. I just started to learn AIML, and wherever I go and go that, I think there is a convolution. So, just give me some idea why the convolution is more. Sounds like everything is convolution, neural network, or so. In what context is a convolution? When I was studied in a undergraduate, I thought that I'm done with that because of the immigration and politics.
Right.
Right now, I think I may have to revisit the politics. So.
Right. So the question is, why is convolution and where is it used that it's become so popular? Now, convolution stems from Fourier transform, and it's one of the methods. And it's find a usage in image processing, and at its heart, it's really multiplication and addition. Two matrices put down on top of each other, multiply, and sum of all of them. And technically, what image processing people are doing is incorrect. It's called cross correlation. It's not convolution. But that term has caught up so much that people are comfortable with it. And if you go to an electrical engineer, somebody working in the circuit simulation, they will tell you that this is not right. But for engineers, what people call is becomes right. So this is one of those things that the right is becoming wrong and wrong is becoming right. So coming back to your question, convolution is only used in image processing. CNNs have found a very successful application in classification, object identification, segmentation, and a number of other things. And so it is used only for images. But when you come to NLP and other branches of AI, convolution is not as popular. And now that you brought up that you studied convolution, you might also know the electrical engineers used it, seismologists used it way before it became popular in image processing. So it's nothing new. It was there in the 60s. It's just the term is catching up so much in media that people who don't study engineering, they're talking about it. Magic or something. Okay.
Thank you so much. Appreciate it.
So one of the problems that early on you must catch on, even though your data set is clean and everything, dimensionality of EDA problems and design automation problem will give you a hard time. And you have to somehow visualize and figure out whether this is specifically for classification problem. So the animation you're looking at, essentially it's doing PC plot and PCA plots. What PC and PC do is they create one point out of your 2,000 or 40,000 dimensionality. So they're reducing the 20,000 points to one 3D point in X, Y, and Z. And when you're looking at that, we as humans, we look at things more visually. The solutions come easily to us when we are able to visualize something. So this is the way to visualize a multi-dimensional problem, reduce it to 3D. And the thing it gives you, if you're working on, for example, classification problem, the distance, the 3D distance between any two points, if it is large, it is an easy problem. If they are combined together, it's difficult to find a plane that separates them. So if I had a plot like this where all the red, blue, and yellow, all of them are combined together, that would be a really hard problem. And this is relatively simple. Now, for convolution neural network dimensionality, this is about 1,800 dimensions, which are reduced to 3. So, analyses like that, before you start working on the solution, would be really helpful. And you need to consult somebody who's done that before as to what kind of analysis I can do to make sure my model would be accurate enough for it to be useful. There are a number of other techniques that can in the analysis. So as part of that, when we solved this problem, we actually embedded that into a characterization platform, which was Guna, and um, there, essentially, this was to identify what kind of cell you're giving it. There are already existing problems for smaller cells, like up to an adder. There are Boolean algebraic solutions that can easily identify, given a fully expected netlist, whether this particular cell is an AND or an OR. So that problem is solved for mostly digital and some of the custom flows, but it is not solved for every design. For example, analog or AMS kind of cells, those algorithms it actually fails. Check my time. So the way we used our machine learning solution was to apply the proven algorithm on the cell first, and once it fails, then we come in. The beauty of that solution was if it fails, you don't have a solution. If it solves, this is a feature, this is a value, right? So the customer will not ask much. And the other feature we had is once you characterize something, it has learned the way you characterize the cell, and it'll use it in the second iteration. So this was the learning the software had using VCC model that we developed. And the VCC feature also adds QA confidence in the models. People who work with these cells, especially library developers, they're always worried about as to my new model is accurate or not, and they spend enormous number of cycles. This would learn whether the last version of the cell for a different node, the same last year for a different node, gave me 18 parts. This time it's giving me 14. What's wrong? What's changed? Functionality is same. Everything else appears to be. So this can flag some of those things. And learning is on the fly. That more data you give it, the better it becomes. So no development or human intervention. So it goes to improve the ease of use. Like you characterize one library one time, 2,000 cells, 5,000 cells, you're done. It'll take you another 3 months to set it up, work it out. But once it's done, the software has learned. The next time you're going to characterize it, it'll require you to do only new cells, or maybe 1 or 2 more cells. So this is one of those things that it improves with time, just like wine. And there are several other topics that I can look up. And this is just one list. Maybe I can take a couple of those and talk about that. I don't have enough time. Anybody has any favorite in this?
So you have been focusing mostly on machine learning. Are there any other aspects of AI that can be applied to EDA?
So machine learning and deep learning, right? The third one that's becoming popular is reinforcement learning.
It's all learning. It's all part of machine learning.
Reinforcement learning is kind of AI. It's not, I would not classify it. No, because it requires an environment. There are no labels or
it's not supervised, but
Sorry.
It's not supervised or unsupervised, but it's still considered part of machine learning anyway.
Okay, but it requires the policy, reward, environment.
Yeah, the model is different.
Right. So there are talks that reinforcement learning can be applied. For example, let's say a successful product like Cadence is what's the best Cadence product? I forget the name. It's a layout designer custom.
Design compiler for Synopsys.
Allegro is PCB. I'm looking more for cells. Virtuoso. Thank you. So Virtuoso, right? It's a very successful product, and it was designed back in 90s. 30 years now. There are a lot of these features that have found the usage in the user base that it's difficult to uproot it. There have been several attempts in the past to compete with it, not successful. And so what you can do with reinforcement learning is make it part of your product and have user watch as to which part of the software is being used in what fashion. And once you have that, environment is given, your steps are given, right? So steps is going from step A to step B. And the way you figure out whether it is long reward or not enough value is whether that step survived in the taped out design or not. If it did, it must be good, right? So you can create some kind of environment to learn from users and create a smaller, lighter product which works on basic machines and things like that. So you can learn from algorithms and also from users using, but the effort requires a large infrastructure change. So I don't know if anybody is doing algorithms like that or not, but there are possibilities.
How much of the problem is that most of the tools in the PPA are sort of functional in AI or
Yeah, those are roadblocks. And how much is it in the real problem? I would only guess. Not all the tools are slow. For example, if you go at the in the front of the flow RTL analysis, relatively fast, right? For a 20 million design, it will give you power analysis within a matter of hours, 4 hours, right? Synthesis, you can do quick and ready synthesis for large, up to 5 million gates in a matter of hours, 3 to 4 hours, maybe 8 hours. So some of them have matured. I would agree with you. Maybe if you're talking about Spice, for example, messages itself, they're not very clear as to what's wrong with my netlist. So going back to your point, there's not much that can be learned. Definitely, the performance comes in the way because if one step is taking 10 hours, you would take many years to create the data set. But then there is synthetic data set that you can create just to get yourself started and start with that. So there are problems, there are solutions. Some of them would be bigger ones. For example, user adoption is definitely a major one. If nobody is using the software, it's going to die eventually. It doesn't matter how good is it and how much has it learned. So I would put that up in the list of higher priority. So let me pick let's say clear value proposition, right? One of the mistakes that people do is
I was going to ask you, which one of these would apply to autonomous cars? Autonomous cars, automatic driving cars. Which one of these would be most appropriate?
Okay, I prepared the slide for design automation context. Autonomous cars, for example, high dimensional array, right? Let's talk about Tesla. They, for their self-driving car today, that they're using CNNs. Elon Musk has publicly said that they're not going to use LiDARs. LiDARs is because their frame rate is very small, like 20 frames per second, compared to their demand, which is over 10,000 frames per second, and until 10,000. I was surprised to know that number too, but it is 10,000. You and I can live with 30 frames per second or 15 frames per second and see it clearly. Cars are moving at a faster pace. So they have to design their chips for the extreme speed. And also look at 6 or more cameras at the same time and be able to process all of that in real time. Right? And so because of the constraint that problem has, dimensionality becomes huge as to what kind of resolution are you bringing in. Cameras today are pretty good. One picture can have 4,000 by 3,000 from a very basic. You can go up to 4K. So every pixel you are adding adds to your dimension. And so you can multiply and come up with a number. In this case, a basic picture would be 12 million dimensions. And that's just impossible to solve for any solution. Deep learning can deal with it, but then you'll require a large network. Training large networks is extremely difficult. So watch out your high dimensionality.
The problem is fixing it out. And we're in that sense. standard cells. If there's any application of AI, using cells, sitting out.
Yeah, so there are attempts.
Repeat the question?
Yeah, okay. So the question was, the question, does it work?
For recording.
No, he can't hear that. So I need to stay close to the mic. Is it better? Yeah. So the question was, can AI be applied to the placement problem, the VLSI placement problem, as we know? So there was a paper a couple of years ago with somebody from Intel working with Stanford on the routability of the cells. And if I remember correctly, that paper created the synthetic data set because of the number of rules, DRC rules and everything that they had to go through. They started with the real data set, but then they quickly converged and figured out it's not possible. So they, however, had a successful outcome on that synthetic data set, and they were able to place cells with high routability. And they were a couple of examples. I personally not worked in that domain, so I would be guessing, but I can only point out that. And I mentioned that in my book too. Stay close to the mic. Yes, sir.
Another application would be design integrity. And I'm thinking of copy name crossing and memory detection, that sort of thing. Is anybody trying? Because typically what happens is you have a whole team working towards tape out, and it ends up gating the tape out. And it's so expensive, and that, a failed chip often will see the stuff. That there is such a high risk that any automation is absolutely effective.
I have heard, and this is just on the basis, probably from that this year, there was a company, very small company, so it's been there for over 10 years. The name skips my head. They were talking something similar. If I search the internet, I will be able to find the name. But
Because the real problem with that particular activity is you could engineer a listing of thousands of pages of bogus warnings. And the issue always is somewhere in the nest, a real issue type. And, so that really seems to be a firewall.
yeah, which is similar to DRC guys. I mean, once you start doing your routing, the first DRC result is always Brazilians, right? So I've seen people sit through their weekends and nights to reduce it to a manageable level before they go home. So it's largely manual, I would guess, but I have no experience.
And the problem is if you see the error, if you see the error, there's so many of them. It's hard to keep your attention for that long. At some point, you just start fading.
Yeah.
And then you've lost.
Yeah, I agree. And there are a lot of problems like that in design automation and flows that design engineers suffer through. That's why they are paid so much.
And somebody, okay, so machine learning, but seeing the pattern in the data. So the problems is they have so much data, and it's not very clear connections, the dimensions, whatever the thing. Those are type of problems it's really easier, but with machine learning. But I want to bring up another one, acceptance of probabilistic result. How much of exactly the opposite work and usually digital design or designing to get everything right. But there's certain elements like a verification involved in the design. But these types of things we have lately with it. Or even certain like temperature, power, failure, all these types of stuff, the more probabilistic we could do more.
Right.
And it's been part of the life. And I think AI might be able to solve some of it. But can we live with that acceptance of
Yeah. So that's a
Can you repeat the
question.
question, please?
Right. So the question is acceptance of probabilistic results. He's hinting that it was a long term.
Yeah, I know.
So I would read that. He's hinting that there are problems that people are actually dealing with, which are probabilistic in nature already. So there's not good enough solution. There's no deterministic solution. So why not go with deep learning instead of brute force method? And is that correct? Yeah. And where is a barrier in that acceptance? And also, can people move to probabilistic results if they are using deterministic ones? So that's the crux of the question. So it's two-part. The first part is easy. I have data. I'm repeating myself here. Statistical results back in 2003 to 2008, there was a lot of money that was invested in companies that did not succeed. So it's been proven once and proven twice in EFM. Probabilistic results, if people have deterministic results, they do not. At least that's what history shows. If and I would not refute if you tell me that if the features or the benefit is so high that they will use. For example, if you tell me that the deep learning model inferencing is 1,000 times faster, they will use it in the first few iterations. So the value is high at the same time. If it provides high enough value, then yeah, the adoption will happen. It will not replace it, but definitely it will be a second choice. So that's that. And the part of the answer for your second question is I agree. Not much to add. If it is probabilistic already, might as well use it. So with that, I don't have much time, so I'm going to move on. We have 8 minutes left, and you guys are waiting for the dinner, so dinner is waiting for us, exactly. So there are a lot of applications that I have a list that I can go on and on, and it's just a matter of your imagination as to how well you can apply any of these, or more of what you can think of in the application of the product that you're working on. It's just it eventually becomes the value and justification of whether it is. So you have to really find a problem that is not being solved yet, and if there's no solution, this solution is good enough. So with that, I have used some of those in our products in the past. So, for example, capacitance estimation at RTL level, where we don't even have a gate level netlist, how you find capacitance, and it was an easy one, and give pretty good accuracy compared to what wire node models are getting. You can generate wire node models, for example, much better than what humans do. So machine learning has a pretty good usage in there, and you can easily prove that too. RC3 estimation is a difficult one, where you have an RC3 and you're using one of the really computing quantum like EWE or LIGHTS or whatever have in the product. It takes longer time, deep learning will faster results, but then it comes back to probabilistic versus deterministic. So and that's of course. So we talked about EDA so far, and I'm going to switch a little bit to the designs, AI designs. So while EDA is busy catching up with these ML and DL technologies, there is another bandwagon that's going on with the AI accelerated chips too. The market for chipsets to address deep learning and training inference workload is relatively young market, like maybe 2.5 years. But the landscape is quickly changing. In the past year alone, there were over 60 companies that were funded of all sizes that have announced some sort of deep learning chipset or IP. So that segment of the semiconductor design is evolving. It's changing very fast. And as of early 2019, this market is close to 7 billion. And it is different reports, and I have given out two references here. One is expecting 66 billion, and the other one is expecting about 95 by 2025. This is a huge gap, like 10 to 13 times in terms of growth in 6 years alone. So, you know, that kind of explains as to why so much money is going into that segment. And this,
You say basic, you really purely find basic, so it's it, or you have to, basics that are sold to.
broad market, combined, everything, yeah. So what this is differentiating essentially is whether the accelerator is coming in the form of FPGA, or even AMS chips. Havana is a company that is coming up with totally different methodology. So these are your points: CPU, GPU, FPGA, SoC, and other. And other includes variety of other chips, right? TPU, VPU, GPU, and there are so many PUs, close to 15 that are coming up for the accelerators. And to put that in the picture, this is the landscape as of August 2019. There are giant companies like Google, Microsoft, Dell. All of them have more than one accelerator in different applications. And then there are the IC vendors starting with Intel, UST. All of them have accelerators. They've announced already. Startups in China and of course worldwide. And the last one is IP design, like IPs, ARM processors and stuff. Broadcom has a GPU that I did not know Broadcom made GPU until I started using Raspberry Pi. And I found out that Raspberry Pi has GPU. So there are a lot of companies that have this, and so now there's a ton of money that's going in these companies, right? Investors are looking at something, and so what is that? What are they looking at? And these four pillars that they are looking at, every one of them, each one of these industries would be well by the chip eventually. Right now, the research is going on, and research is progressing at a faster rate. And for you to be able to justify to create a hardware for an algorithm is to make sure that your design would not be out of date because new algorithm showed up that is faster. So the investment you made in the design is gone well yet. So people are kind of waiting for the research to stabilize, and I can give you one example. For example, image processing. Last 2 years, there's not much that has happened. I mean, after 2016, the top 5 error rate, once it came down to 3%, there might be improvement, but 3% to 1.5% will not break the limit. We can live with it. It's already superhuman accuracy. So it's safe bet to start the company vision. If you are designing a chip, it's safe bet today. But if you are doing something, let's say in the language or NLP, the things are churning out at a faster rate still, and it's not stabilized by any means. So that would be one of the criteria. So now these four pillars of this growth, and all of these are several hundred billion industries. Some of them are going to bring out new applications, and some of them will be disrupting the existing applications or augmenting. So with all of that combined, and everything would be fueled by a chip eventually. That's where the investment would go, and that's where the growth projections are coming. Again, opportunity. So what does this give us? Now that we know so much investment is going on, where would you start working on, right? Chips are being designed, and every chip would require a compiler, some sort of framework. If it's an edge device, edge chip, then you would need, if it's low end, for example, generally edge devices are low end, low power, then you would need some kind of compiler to load your deep learning or AI model onto that. So there is opportunity there. It will create more jobs. So design engineers and compiler engineers will be in high demand for a few years to come. And there are several opportunities that it's, so what we are doing at AIDS, we are building compiler. Now there are companies out there who are also doing compiler, like Google, right, with massive deep pockets. Why would we want to do compiler and go against Google or Facebook? Now what they are doing is essentially orthogonal to their business. Google is hoping to ramp up their cloud business using TensorFlow and their variant. So they are giving that as for free, and they're hoping that people will come to their cloud and use their models because TensorFlow is so popular. Now that will give rise to services, and they will use that revenue in the Google cloud. So there are these orthogonal business interests that are driving these companies that are making you believe that they are doing some kind of community service. It's a strategy that's being well found, stealing from Peter and giving it to Paul kind of a strategy. And what we are doing here is, it's an open source project. We are looking at very tiny, small microcontrollers that are part of your refrigerator, your washing machine, everything that you have today. They're like $3 to $30 small, tiny chips that are so reliable, so inexpensive, and part of household devices. Think appliances like cars and toys. In fact, there are about 30 billion microcontrollers, power devices that are produced every year, and nobody's looking at that market. The reason is they haven't found the angle that would serve another arm of their business. So we are looking at that segment and saying we will bring down these models and make them run on little tiny devices. And this is open source. So you can go that, the heading is your URL, bit.ly/DNN compiler. You can go and download that today. So they're cheap. All these microcontrollers are cheap, require very little energy, they're very reliable. And by bringing deep learning models to these tiny microcontrollers, we can boost the intelligence of billions of devices that we use in our lives without relying on expensive hardware or expensive internet connection. Imagine smart appliances that can adapt to your daily routine, intelligence, industrial sensors, and understand the difference between problem and the normal operation. And the magical toys that can help kids learn fun. So, again, yeah, we're working on that. But there is a framework that's available today. We are delayed by a couple of weeks. You have it ready by the end of. So this is well by a community. Everybody is working part time, and all the source is open source. You can look at it if you feel like downloading, use it. We will help you, community that help you. If you would like to participate, you're welcome to participate. So why another compiler, right? In the case of these guys, we're doing over $70 million revenues and whatnot. Like I said, no, they have not figured out in their business strategy how to power these devices and how to benefit from that. And ours is a proven computer. So we looked at a variety of these frameworks and tried using them to our purpose. The effort that we estimated was way larger than coming up with a compiler on our own. So otherwise we were going with TensorFlow because it's the best and most popular repository and printer. It is slow, it will not have sufficed to our performance objective. And also training new people on TensorFlow is like sending people to Mars, almost. So it's very clunky, very large software. We gave up on our efforts and started this. If you have any questions, feel free to come ask me afterwards or after dinner or whenever I do. Thank you very much. I think I I did finish on time.
Thank you so much. And now we have a break.